We say what? Okay. So again, we're going to solve now the first one here. Now what I'm going to do is, as you can see here, I'm factoring all the numerators and the polynomials first. You could multiply first and then factor. That's fine. Excuse me. You could do that if you want to. Multiply, then factor. I'm doing it first. And, you know, it really doesn't matter that much. In the end, if you do everything right, you'll still get the right answer. So if you have x squared plus 2 times x minus 8, right? So again, so for this one, excuse me, we want two numbers here, right? Whose product is negative 8, and the sum is 2. Right? There's 3 terms, the trinomial that is, degree 2, leading coefficient is 1. So we want two numbers whose product is negative 8. Okay. Negative 8. The constant term, the coefficient of x, we want the sum to be 2. Okay, what numbers do that? Well, how about 4 and negative 2? And we get that. We have x plus 4 times x minus 2. So 4 and negative 2 work. Their product is negative 8. The sum is 2. So their product is, so that works then. We get this. Here, we want two numbers whose product is minus 20 and whose sum is 1. So what numbers? How about 5 minus 4? That works, right? So what do we do next? What we can do is so those numbers work because their product is negative 20, their sum is 1. So we have this. And same here for the last one. You know, the product, we want two numbers here whose product is 4, whose sum is 5. Let's use 4 and 1. So we get this. Again, we can do this with all of these because all of them are trinomials. They all are degree 2. They all have leading coefficient 1. So when we put all of these in here, like so, this is what we get. As you can see, just that. Okay. Now, so once we do that, then we can actually multiply. Okay. Again, you could have multiplied first and then factored. I decided to factor first and multiply. So I mean, I probably should have been more consistent in these examples, and I hope it's not causing more confusion. From here, we multiply, then we get this, right? And you can see that there will be some cancellation. On top, we have x plus 4, same thing on the bottom, those cancel. And it looks like that's it. So this is our answer. All right, that's good. Okay, so the next, are there any questions about this? Yeah.
For the top, is it supposed to be x minus 2 instead of x plus 2?
X in the top, let me see. X squared plus 2x minus 8. Yeah, thank you. Let me fix that.
Okay, I just wanted to make
No, that's okay. No, I'm glad actually someone pointed that out. So someone found that in me. Let me just fix that for you. Beautiful. Thank you. Awesome. Any other questions? So now everyone can, okay, so that example is done. Okay, awesome. Good. Now for the next one, it's really the same idea. I mean, what I did again was I factored everything first, then I actually divided. So from here, We have x squared plus 2x minus 3. Okay, so again, we want two numbers whose product is minus 3, whose sum is 2. Right, again, we have three terms in this polynomial. Its degree is 2. The leading coefficient's 1. So we get x squared plus 2x minus 3. So to factor it, we have two numbers whose product is minus 3 and the sum is 2. What numbers do that? Well, how about 3 and negative 1? So we have 3 and negative 1, so we use those. And you could easily check that that works. We also have this here, x squared plus 8x plus 16. Okay. So from here, right, we want two numbers whose product is 16, the sum is 8. Well, what numbers are going to pull that off, is 4 and 4. Again, we're factoring this way because we have three terms. The leading coefficient is 1 as well. And it's degree 2. So again, two numbers whose product is 16, whose sum is 8. That's this. We have 4 and 4, so we do this. And 3x plus 12. All you really can do here is you can factor out a common factor of 3 among the terms. And that's what I'm doing. We have 3. We factor 3 out, dividing, we get this. So once we do that, okay, what we have then is this with that quotient. Again, I factored everything first. I mean, you could divide first if you wanted. It really doesn't matter that much. What we do here is we flip, as you can see, right? We flip. Then we actually multiply. And from what it looks like here we go, sorry. We actually can cancel a bit, right? There is some cancellation that occurs. You know, the x minus 1, it looks like cancels. And it looks like x plus 4 does as well. Hopefully I didn't make it. I don't think I made any of this. So we get this. And so from here, we get x plus 3 times 3, or 3 times x plus 3, excuse me, over x plus 4. So this here is what we get. All right, that was fun. Any questions on this one? Okay. All right, so that's what multiplication division. What we can also do with these rational expressions, we can add and subtract them. We can add and subtract rational expressions. Just like with rational numbers, we can add and subtract them. The thing is, though, you have to have a common denominator. You know, the denominators have to be the same. And if they are, you just add or subtract the numerators. That's it. Now, with these rational expressions, just like with rational numbers, okay, there is a most convenient choice for a common denominator. I mean, theoretically, you can use any denominator you want as a common denominator. But the least common denominator, which is also the LCD, that's really the best choice, mostly because you'll have the least amount of simplification to do at the end of the problem, that is. So that's why I want to focus on the LCD. And again, what is the LCD? Well, it's really the least common multiple of the denominators. Or in other words, polynomials, it's the polynomial of smallest degree that contains each denominator as a factor. So again, it's the polynomial of smallest degree that contains each denominator as a factor. And that's just the definition. That's all it is. So to find the LCD, okay, so we know what the LCD is. Okay, it's the polynomial of smallest degree that has each denominator as a factor. How we find it is actually here. Essentially, you're going to factor completely each denominator. For each irreducible factor, you'll list them. You get the biggest exponent among the denominators that factor is raised to. Raise it to that biggest exponent, and then multiply them together. I know that's probably really confusing what I'm saying and what I have written here. When we do examples shortly, we'll see what it will make more sense. Just do this recording.